Well, students, good morning to all of you. In my last class, I had told you regarding stability. But before stability, I had told you something regarding the feedback control systems. In any feedback control system, there is a reference input which is given to a comparator. This comparator output is going to a process, output CS. From the output CS, it is coming back via feedback system to the comparator. And the error signal which is generated due to difference of the reference input and the feedback system, the output which is coming is the error signal, and this error signal will go and act on the controller, some controller, maybe PID controllers. So this feedback system which is giving you an output, this output may be stable or unstable. So my today's topic is regarding stability criteria, and that criteria is Routh Hurwitz criteria. Okay. Now, as regards stability, in my last class I had pointed it out that what is a stable system and what is a unstable system. Any system whose output is increasing continuously with time is known as a unstable system. On the vice versa, if any system whose output is decreasing with time, for example, it is the highest and with time it is coming down and it becomes state, which will make the system as stable. But I also told one thing, that there is a small error as time t tends to infinity, which is governed by FVT, that is the final value theorem. In my present lecture today, I will be taking Routh Hurwitz criteria based on which stability can be determined, but we can only say whether a system is stable or unstable. We cannot say how far the system is stable. This is loophole, yeah, which we will cover in our next criteria, which is the Nyquist criteria, maybe both plots and later on. So today's topic is my feedback control system, Routh Hurwitz criteria. Now, when you come to Routh Hurwitz stability criteria, this method is to determine continuous system stability. But what the criteria says? The criteria states that the number of roots of characteristic equation with positive real parts is equal to number of changes in the sign of first column of the Routh array. Students, very important. You have to see in the Routh array, in the first column, any sign change is there or not. Only this much you have to ascertain. If there are no sign changes, the system is perfectly stable. But if there is a sign change, maybe one time or more times, the system becomes unstable. But before that, we have to see how Routh array is framed, which I will show you with the help of certain examples. Yeah. We will also see the difficulties faced, the two difficulties faced, case 1, case 2, and what is the remedy for it. I will also come back to it. Okay, let's come further. So, Routh Hurwitz stability criteria. This method yields stability information without the need to solve for closed loop system poles. Please student note that it can tell how many closed loop systems are in left half plane, in right half plane, and on j omega axis. But most important is that we can say how many, not where. That's very important. So this method requires only two steps. The first step is generate a data table which is called a route table. Second, interpret the route table to tell how many closed loop system poles are in LHP, left half plane, RHP, right half plane, and on the imaginary j omega axis. So we will see now what is the Routh's stability condition. If the closed loop transfer function has all poles in the left half of S plane, the system is stable. Hence, in that case, there are no sign changes in the first column. Also, Routh criteria declares that the number of roots of polynomial that are lies in the right half plane is equal to number of sign changes in the first column. Hence, the system is unstable if pole lies on the right hand side of the S plane. So you already know that all the poles have to lie on the left half of S plane, then the system is stable, and vice versa, it becomes unstable. Okay. Now, to generate a basic route table, if we take RS as input, C as an output, and transfer function as this. So we see here it is a fourth order characteristic equation. Characteristic equation is the denominator of a transfer function. We have already seen. So we have to write any characteristic equation in the reverse order of S to the power of that equation in the reverse order, decreasing. So in this, when we see here, it is s to the power 4, s to the power 3, s to the power 2, s to the power 1 and 0. So we are writing in the decreasing order first. Okay. Let's take example 1. Consider the following characteristic equation. S4 plus 2s cubed plus 3s square plus 4s plus 5 equal to 0. Now, in order to develop the Routh array from this characteristic equation, please see s to the power 4. We write first row as all the even coefficients 1, 3, 5. Similarly, in the second row, we are taking all the even numbers 2, 4, 0. Now, how to calculate this row S square? Please see, we multiply 2 into 3, 6, minus 1 into 4, 4 divided by this 2, which gives you 1. Similarly, it will be, for this you find it out as 2 into 5, 10, minus 1 into 0, 0, divide by 2, which gives you 5. Similarly, we can find this and 5. Now, the beauty. What is the beauty of Routh Hurwitz criteria? As we go down in the decreasing order of S, we see that number of coefficients keeps on reducing and zeros goes on increasing. Please note. Here 0, 0, 0, 0, 0, and coefficients was highest here, and as you went there, the coefficient reduces, but zeros keeps on increasing. Example 2, if you see, consider the system, RS input, CS output, and take the transfer function. Same way, the highest order is 3. So we are taking S3, S2, S1. Okay. 1, 31, 0, again 1, 1, 0, 3, 0 and 0. Now if you divide by 10, 10 1 are 10, if you do 1, 0, 3 and 0, now it becomes easy for solving. Please see how we are taking the absolute value, the determinant of it, 1, 31, 1, 103 here, divide by this coefficient which is 1. Same way, 1 into 31 minus 1 into 103 gives minus 72. Same way, calculated 0, 0 and rest of the coefficient is 103, 0, 0. Coming to example 3, find the stability of the quantity system having characteristic polynomial of a third order given below. S cube plus S square plus 2 plus 24. Same way, students, S cube 1, 2, your odd, then S2, again even it will come, that is 1 and 24. Same way we are seeing, but please see in this example. The first example which we had seen, and now in this example we are seeing that there is a only one negative is coming, negative sign. But can you tell me that how many times sign has changed? It is 2 times. How? First from plus to minus, 1 time sign change. Again from minus to plus, second time sign change. Thus 2 times sign change is there. Please see here. 1 plus 1 to minus 22, 1 time sign change. And from minus 22 to plus 24, second time sign change. Thus 2 sign changes appear. Hence system becomes unstable. If all these would be positive, here will be no negative, then the system would become stable. This is how the Routh Hurwitz criteria stability is determined. It means your first column, that is first column, all the coefficients should have the same sign, all positive, it is stable. If any one or more sign changes, then it becomes unstable. Example 4. Determine a range of values of system parameter k for which system is stable. S cube plus 3 square plus 3 plus 1 plus k is equal to 0. Okay. S cube 130, S square 3, 1 plus k 0. 8 minus k by 3 0, 1 plus k. For system stability, it is necessary that the conditions 8 minus k should be greater than 0 and 1 plus k greater than 0. If we combine these two, it gives k line between 1 and 8. So between minus 1 and 8, it will give you a stable system. Now, as I told you students earlier, there are two cases arising in this. Case 1 where Routh criteria fails and case 2 also where it fails. But first case where it fails, we have seen that while dividing the numerator, if anywhere it is 0, then it becomes indeterminate while dividing. This is failure of Routh criteria number 1. Its remedy? Yes, very simple. If you could just take this 0 as epsilon, some value, alpha, beta, gamma, delta, anything, and this alpha, beta, gamma, what you are taking, epsilon, tending towards 0, and we can go ahead further as Routh array says. It is solved. Case 1. Case 2. If all the elements of any column is 0, then again your Routh criteria fails. Its remedy will be, we will make a characteristic equation based prior which is making 0 and differentiate it, and after differentiating, its coefficient is taken and we proceed as usual in Routh array. Okay, let's see by example. Case 1, 0 in the first column. If first element of a row is 0, division by 0 would be required to form the next row. To avoid this phenomena, 0 is replaced by a very small number, say epsilon, and this epsilon is tending towards 0. Example 5. S cube plus 2s square plus s plus 2 equal to 0. Again, writing the same way, 1, 1, 2, 2. But this 0 we have taken approximated as epsilon. Example 5. Qs equal to s to the power 5 plus 2s to the power 4 plus 2s cube plus 4 square plus 11 plus 10. Now Routh array can be formed as follows, as we seen earlier. The only thing is where it was coming 0, 1 into 2, 2, minus 2 into 2, 1, 0, 2 minus 2 becomes 0. This 0 is replaced by epsilon. Here 2 into 2, 4, minus 1 into 4, 4, 0 divided by 2 becomes indeterminate, hence epsilon has been taken. And we proceed further as we used to proceed in our Routh array. Please see C1, how you find out. 4 epsilon minus 2 is 12 divided by epsilon, that gives you minus 12 by epsilon. D1 is 6 C1, 6 into C1 minus 10 into epsilon divided by C1 gives you plus 6. Thus there are two sign changes again, and this makes the system as unstable. Okay, so let's come to example 6. You have to determine the range of parameter k for the system is unstable. Similarly, we see to form the Routh array 1 1 k 1 1 0 same epsilon and minus k by epsilon it is coming. Therefore, the system is unstable. Why? There is one time sign change minus here. So 2 times sign changes, plus to minus once and minus to plus 1. Okay. Now, let's come to next example 7. If we determine the stability of closed loop transfer function 10 upon s to the power 5 2s 4 plus 3s plus 5 cube, if we take as characteristic equation this, form the Routh table 362 531 from here, and then again how to find out this? 5 into 6 minus 3.3 into 3 divided by 5 gives 4.2. Similarly, rest we can find. There are 2 times sign changes. One from plus 1.33 to minus 1.75, 1 time sign change. Second time minus 1.75 to plus 1 is second time sign change. Thus 2 times sign change, this makes the system as unstable. Well students, I hope you have understood this case 1 where when it is 0, epsilon is to be taken, this epsilon is tending towards 0. Okay, now we are coming to case 2 where entire row is 0. Entire row is 0. Sometimes while making Routh array, we see that entire row consists of the 0, right? So what we are doing in this case, if we are making case 2, it is entire 0. How to determine the stability? For example, we take Qs is equal to s2 plus 2s plus 4 plus k. If we see here in this case 1 4 2k